Hello and welcome back to California Geology. I am Dr. Robert Lopez, and today I want to talk about metamorphic rocks. Now, metamorphic rocks, the key thing is that it occurs in the solid state. If you get it too hot and melt it, then you've left metamorphism and you've entered the realm of igneous rocks. Now, the meta part of metamorphism means change, whereas the morph means shape. Now, the important thing metamorphic rocks tell us is that they provide clues to past tectonic environments, what pressure conditions could have existed, temperature conditions. So they're all clues to geologic history. Now, the word protolith refers to what the rock was before metamorphism, sort of the parent rock before it was metamorphism. For example, limestone is a protolith for a metamorphic rock called marble. So when limestone undergoes metamorphism, it turns into marble. Now, there's several types of metamorphism, and here I talk about two. Actually, I'm going to have three here, but the two general ones we talk about are contact metamorphism and regional metamorphism. Now, contact metamorphism involves a local heat source, like an intrusion of a magma that burns or bakes a surrounding country rock. And usually we call that a hornfels. So hornfels is kind of a burnt rock occurring at a contact metamorphic zone. We'll say more about hornfels here in a little bit. And in the High Sierra Nevada, because the batholith had many plutons, many magma chambers intruding the country rock, it has a metamorphic roof pendant, or an area around the batholith that experienced this contact metamorphism. So we'll talk about the roof pendants in the High Sierra. And usually you'll get, because the magmas are hot and they're making their way up to the surface, we see a high grade. And so this term grade here refers to temperature. So whenever you see metamorphic grade, we're talking about temperature. So a high grade means high temperature, but it's at relatively low pressure because the magmas have been moving up. So that's kind of a unique setting for that type of metamorphism. Now, the other big metamorphism is this regional metamorphism. And regional metamorphism, in this case, the heat source is not specified. It could be deep burial. It could be how close the rock is to an intruding batholith or magma chamber. Kind of like the Sierra Nevada foothills has experienced regional metamorphism. And also it involves lots of pressure, like a subduction zone. In fact, sometimes this is called subduction zone metamorphism because there's very little heat. Note that there's low grade because the rock is cold, the oceanic lithosphere is cold, and it's being pushed into the mantle. So you're getting high pressures at a relatively low temperature, low grade. And so our California coast ranges have a lot of rocks that have experienced this type of metamorphism. Now, in terms of this hydrothermal alteration, well, this primarily is occurring at mid-oceanic ridges where seawater percolates into the ocean lithosphere and alters the rock, and it often alters the mantle rock there, and we make the California state rock called serpentinite. So serpentinite is really a metamorphic rock whose protolith was peridotite. All right, so let's look at California and metamorphism. So we'll look at a map in your book here in a moment. But California, there's an important formation, a world-class formation. People from all over the world come to look at this formation because it represents a subduction zone. And that's exposed all over the coast ranges, this Franciscan formation. So let's put coast ranges here. And what's interesting in the California coast ranges is that this Franciscan is exposed only to the east of the San Andreas Fault. So there's a story there that we'll have to tell later on. But Franciscan formation, again, low grade, but high pressure. So that's going to be our subduction zone, subduction zone where we're seeing this cold ocean lithosphere being pushed into the mantle. Once it gets down there, it warms up a little bit, but it's still, you're going to have lower grade than you should have at those depths within the earth. Now, as we move over across the Central Valley to the Sierra Nevada foothills, the western foothills belt, we find this metamorphic belt. The rocks there indicate that they've been metamorphosed at a medium temperature, medium grade, and also a medium pressure. So they're telling a story there as well. And then as we go to the high Sierra, above Yosemite, the higher peaks, we find that those rocks in there, the ones that are the older metamorphic rocks, they've been metamorphosed at high grade, so which means that the hot magma, this intruding batholith, has burned these rocks at low pressure, and so these are going to be our roof pendants, and they're called a pendant because they occur at the top of the magma chamber, sort of like a pendant. Now, let's look at your book here. We'll look at this map. So on the inside front cover of your textbook, one of the questions I ask you to know is, on a map like this, a geologic map of California, be able to locate the Franciscan Formation. And the Franciscan Formation is this light green color. You see it's all over the Coast Ranges, and then you can see right in here there's a straight linear feature. That's the San Andreas Fault. And note that the Franciscan is exposed only to the east of that San Andreas Fault. You see a little bit of Franciscan over here in the Big Sur area going down towards San Luis Obispo, and that's because we have another fault line there called the Sur Nacimiento Fault. And interestingly enough, the Franciscan is only exposed to the west of that fault. So we'll have to talk about this block of rock that exists. In fact, that's part of our field trip. We'll look at the Selenium block here and decipher its history. So anyhow, Franciscan here in the Coast Ranges, and then here's that western foothills metamorphic belt. And then some of these rocks up in the high Sierra have experienced the roof pendant metamorphism here. The red rock here is the granite. That's actually the Mesozoic batholith granitic rocks. All right, let's look at this pressure temperature diagram, because we can explain the whole story here just looking at pressures and temperatures. So this is similar to the figure in your book on page 31, figure 2-5. And what we have on the x-axis, we have temperature, and on the y-axis we're going to go down in pressure here. And so what we want to show here is show some of these zones of metamorphism. And so anything really less than 300 degrees centigrade here is considered low grade metamorphism. Whereas 300 to 500 over here is usually considered medium grade. And then greater than 500 over here is going to be high grade. Note that it depends on the rock type. Some rocks will melt at lower temperatures, some melt at higher temperatures. So once you get too far over here, we can sort of put a line over here. We start seeing igneous, we start seeing magma over there. So we've left the region of metamorphism. Now, there's three fundamental paths on this diagram. This one up here, we can call it the low pressure, because we're at relatively low pressures, but we have high grade, so we can go to high temperatures. So the only place that can happen is if magmas come up and burn rock up near the surface. So we call this hornfells. So out here we're going to see the hornfells. And hornfells are classic contact metamorphic rock. Hornfells. Now, in the Franciscan Formation, at a subduction zone, we'd expect to see very high pressure but low grade. So we start to stay in this low grade field. So there's going to be low grade, low temperature, and high pressure. So that's what we expect to find in a subduction zone. So we'll put subduction here. And these rocks have an important name as well. Like hornfells, these are going to be called blue schist. And literally the rocks are blue schist. And then as we go over here to this normal grade, normal pressure, that's what we call this middle one. In fact, let's just call it normal grade and normal pressure. Normal pressure. And it's more of a gradual. You're getting closer, more proximal to that heat source, which may be a batholith over here. In fact, the igneous rock over here. So we can put the batholith over here. And that would be where our heat source is coming from. And so the closer you get, the higher the grade. Now, there's a couple of fields in here. One of the ones I want you to know is a field called green schist. So right kind of in the medium pressure, medium temperature, we're going to have a field here called green schist. Green schist. And the green schist metamorphism occurs at about medium grade, medium temperatures, and about moderate 10 to 20 kilometer depths, green schist. Once you go pretty far down, there's a field over here called granulite. And granulite facies, remember, a facies defines a group of rocks or minerals that specify a pressure temperature conditions. So we have hornfels facies, green schist facies, blue schist facies. Granulite facies describes high pressure, high temperature. Usually this is occurring near the roots of a batholith, or maybe where two continents are colliding. We really don't have very many granulite facies rocks in California. There's some up down in the Big Sur area around Cone Peak, but really there's not a whole lot. Now, so these are our paths of metamorphism. This high pressure, low grade is typical of the coast ranges. Here's our Sierra Nevada foothills, and then our hornfels facies would be at the high Sierra. So in the next segment, I'm going to talk about how these are related to the cross section of California.